Okay, hello everyone to 295 on causal reasoning. Today, Donko will talk about the paper by Sander Greenland on causal foundation of applied probability and statistics that is part of the ACM volume. So the floor is yours, Donko.
Thank you. Thank you for the introduction of the paper. Yeah, as she said, the paper I'm going to present today is the causal foundation of applied probability and statistics by Sander Greenland, 2021. Basically, the paper says that scientific inference is
just a comment. You may want to go to a presentation mode for your slides. It's
okay.
It's not if you want.
Yeah.
Just there is this. You can just click.
Yeah.
Okay.
Okay, give me a second.
If you prefer the other mode, that's fine too. It's up to you.
Yes, it will be easier for me, more familiar to me.
Okay. Yeah, you can go to the other mode. That's no problem at all.
The paper argues that scientific inference is a branch of causality theory. So statistical theory has been developed focusing on or recognized as a branch of applied mathematics, such as probability theory, but causal theory is essential for statistical science. It means that the application of statistics should consider causation if it is to represent underlying reality from the observed data. That is because every real-world data analysis has a causal component with an underlying network, causal network, generating the data, even for the descriptive analysis. We'll see an example of that part later in this presentation. And furthermore, of course, for the decision analysis, such as treatment analysis, showing the effects of the decisions or treatment requires design strategy to rule out alternative explanations of the observation. So from these points, the author argues that causal theory is not extra statistical, but it is essential part for the statistical science. So causality is not extra statistical, but instead it is a logical foundation of statistical analysis. For example, if the claims of random or unbiased ignorable sampling requires causal actions to block unwanted causal effects on the sample patterns. Without such causal analysis, independence assumptions can only be treated as subjective assumptions that has to claim no compounders affecting selection and outcomes. Incorporation of causality into introductory statistics from study design to data analysis is urgent necessary, which is the main argument of I believe of the author. So probability cannot be an adequate foundation for applied statistics. So statistical practice integrates logic, context, and probability into scientific inference and decision using causal narratives to explain diverse data.
Can you explain what you said, what is the points, the first 2 points on the slides refer to when you say claims of random, unbiased, ignorable sampling requires causal action to block, no, in the previous, yeah.
Here?
Yes. It requires causal actions to block unwanted causal effects on the sample patterns. Can you explain what that means?
I think it is easier to use the example from the paper. This is
okay.
this part, yeah.
Okay.
There is that part.
Go ahead. Okay, go ahead.
Yeah. Even for the purely descriptive goals analysis, causality is the center. This is the example of that part. Consider a survey analysis about the proportion of voters who would vote for a given candidate. It seems that it does not have causal part in that analysis. We can see that the distribution of the preference of the voters' preference for different candidates. However, even this descriptive analysis has causal component. Think about some characteristics C may affect both survey participation and voting intent V. The example from the paper is affinity, or can be income or other parts. If that characteristic affect both survey participation and voting, the voters' preference for the candidates, then it may cause biases of the voting patterns in the samples representing the real unbiased, the real voting preference in the population. Let's see this causal graph. C is the characteristic, S is the selection node, V is preference to the candidates. We only can see the samples observed S is equal 1. It means that this node always conditioned. So if the distribution of the characteristic is different between observer sample and the population, then the observed distribution of V is different from the real world, the population. So the probability of V given S equal 1 is biased for the probability of V. So the causal relationship from C to S causes kind of biases for these descriptive studies. So this is an example of that part.
Okay. I'm trying to understand the notation. S is a variable that say participate in the survey. S participate in the survey, right?
Yes.
And S equal 1 means you participate. S equal 0 means you did not participate, right?
Exactly.
So, there are some characteristics that causes both influence participation and voting. So let's say people who participate in the survey vote for one candidate. Likely to vote for. And since C is not observed, you are saying C is not part of the answer, you cannot see that. So what you get, we have the confounding thing that we are getting. So the observations indicate the observations are conditioned on S equal 1, but we don't know that. Is that the case? So I don't understand the sense that S equal 1 indicates the observations are conditioned on S equal 1. What does that say?
Yes. Let's.
So is it saying that a person selected to take a survey? This is what I would think, but S equal indicates, I don't understand the sentence. I tried to read also the paper and I had the same difficulty.
Yeah, give me a second.
It's a selection bias. Understand what selection bias is. It's a person, you have characteristics that influence whether you are doing the survey or not.
Yes. So,
yeah, go ahead.
By this part is clearer for that part. By definition, we can only observe the observed sample. So that means that that means the S equal 1 is always conditioned on. We can see the samples S is conditioned on. That is by definition of the selection node. So if some other characteristic affects whether the sample is observed, for example, let's say that C is income, and people who have higher income, let's assume that people who have higher income has more intent to participate in the survey, maybe because they have enough more time to participate in the survey kind of thing. Then the observed sample have more people who are rich, and they are more preferred to one candidate than the other. So the distribution from the sample will not represent the distribution of the voters' preference in the population. Okay. So that is what is
okay. I understand. So why won't you go back and let's see? Let's go back to the slides where we were. The first, what are the slides? The slides that we stopped with the S. Where is it?
Here.
No, the third. Go to the third slide.
This
one. Where you have S equal. No, the next one where you had the example here. Yeah. So just to summarize, this the author is just trying to argue what we know, that if there is a confounding variable that influence both the survey and the variable, and we are not including it in the model, don't know about it, we can get very bad, very biased results from the data. And this is when we know that, but he's trying to argue in this paper what we in the class we took it for granted, but now he's talking about from the viewpoint from statistics, because the statistics theory sometimes rejects causal reasoning in some parts of statistics, or they say that it's not necessary. So this is an example that even in these simple cases, if you don't consider the confounding or you don't have data, that's a problem. I just was not sure about exactly the notation here, but that's fine. Okay, go ahead, continue.
I had a question here. I understand the argument here is that you need to take into account the confounding variables in order to unbias your samples, right? But what does that seems right, but what does that have to do with causality, right? Because you could just think about this as a Bayesian network, right? Where we're just talking about probabilistic relationships between our variables S, C, and V, right? And how the network encodes certain independence assumptions. Like, why do we need to move to the causal interpretation where we're talking about interventions on our network in order to account for this problem? You see what I'm saying? Because like here the issue is that, right, like you have the fact that S and V are not conditionally independent of one another because there's the confounder in the background, right? But once you do condition on that, you can get the desired result. You know, you don't need to appeal to any sort of notions of like intervention or whatnot at that point. So I'm just curious, like what about this requires causal reasoning?
I think that's a great point, and that is what the paper want to say is basically this example seems seemingly are no causal component in the analysis. However, even this simple analysis, we have to think about some causal part to derive applications from unobserved data. That is that part. And the author argues that even for the conditioning to remove the bias part or some other reweighting technique, which is proposed in this paper to adjust that bias, is a causal process.
Yeah. So I think, I mean, I want to support what Danko said. I think that when statisticians are saying confounding and condition, they are doing it engaged in a causal argument. They are just not saying it explicitly. But that's when you are saying confounding, you are saying that there is something else that influence in the data, in the way the data is generated, that you acknowledge, which is in the process, and you correct for that, and they do that. But we know they do that just because they acknowledge that it exists. And acknowledging that it exists is assuming a causal model, assuming that there you have this structure, C causes S and causes V. So if it was a Bayesian network, so I mean, if you could assume that the data was received from an unbiased, population without the confounding, maybe that, and this is done in randomized experiments, I guess. But that's I think what he argues here. Am I right, Danko? I mean, is that your understanding? So does that make sense, Bruce?
I understand that, like the statisticians, maybe the statisticians do think about like have causal reasoning in the background when they're considering unbiasing their data. But mathematically, I'm just thinking like this, if you view this relationship just in terms of a Bayesian network, and you are exact in specifying what you mean by causal reasoning, which is where you want to find the do relationships that hold between operations on variables and their distributions. Here, you don't need to do any do to figure out like your data is biased. You can just talk about it strictly in terms of the conditional independencies encoded within the Bayesian network. That's all.
But you're saying Bayesian networks in this networks that you have here is causal. It's not a pure Bayesian network. It's assumed this relationship, and if you went in a different direction, I don't know. I don't know that the point here is that you have to think about this third variable and to think about its relationship. And whether you call it Bayesian network or a causal network, the actual confounding here is because it's causal and not because you can, it's associated with the fact that the Bayesian network will have the same structure if you go in that direction. But I don't see exactly this issue. But anyway, let's move on and see if this is clarified.
Okay.
But I do think that that's the point, at least now, that he's making right now. Okay, go ahead.
So we already talked about this part, but we can remove that bias, selection bias, by reweighting the sample using target population affinity C distribution. But it is also a causal process that needs to obtain target weighting data and program the weighting to make the adjusted estimate. So we have kind of new causal diagram with a reweighting procedure. This is the sampling procedure, and however, the C can make bias between S and by the path between S and V. So we have to reweight that part by another part of the diagram with a weighting intervention W to adjust target and population distribution and obtain the unbiased distribution of V, P, V equal V. So this the author argues that this process is a causal part on the unbiased estimator from the observed data. So this is one of the possible solution for the bias.
So the variable C appears twice.
Yes, but
it's the same variable?
Yeah, same variable. But this is just to kind of to represent this relationship. I think that is not. The paper says something about that.
So when they say W has an arrow into V, so that what they are saying, I think what he's saying, and let me tell me if I'm correct, is that statisticians acknowledge this issue. So what they do, they know that there are confounding aspects. So what they do is that when they are taking the survey and they look at different values of S equal 1, S equal 0, and for each one, they have a weight. I'm not sure I understand this procedure.
So
target weighting data, what is the process that they are using now?
For example, in the sample, I believe what I understand is in the sample, there are 7% of rich persons and 30% of poor people. However, in the population, we need to another survey or another data generating process about the distribution of the characteristic in the population. And if we found that the population, the distribution of the C in the population is 50 are rich and 50 are poor, we need to reweighting the distribution to adjust the estimate for the V distribution. So that is the reweighting part in here.
So if they got a survey only from people that are rich, okay, let's say they got the survey, so the survey is from people who are rich, and the number of so they will be 1. The percentage, and let's say that if you're rich, you're voting for candidate number 1, just in extreme case. And if rich people are 30% of the population, they will say it's the probability of voting for this candidate is 30%. That's probably, that's, and if so, they will look at each, okay.
I'm not familiar with the statistics of this, but I mean, what would make sense to me is if rich people make 30% of the population, but they make 80% of the voting, then maybe they would reweight it so it kind of represents 30% instead of 80% is like what might make sense in my mind.
Yeah.
They correct the, okay, but okay. But I don't see how, I mean, this diagram reflects what you just said. So that's, I think it makes sense that this is the process, and he's trying to argue that this process is actually as if you assume this causal diagram that we see here. So it's there, in that sense, it's also a causal. So I think, I'm not fully sure, but let's proceed. I think what we understand that what he's trying to show in these two examples that we, or this evolving example, is that certain ways that statisticians are working could be interpreted as if they're having some causal diagram behind the scene, right?
Okay.
Is that, am I correctly interpreting what he's aiming to show?
Yes, I think so. Yeah.
Okay. Okay, let's leave the fact that at least I don't see the diagram as reflecting that to future deliberation. Let's see if we will get that, understand it later. Okay, you can continue.
Okay. And then the author says another kind of example about the probabilistic independence demands physical independence. The data generating process in the previous example does not mean some abstract structure equations behind it. Even for the simple coin tossing example has that part as well. Consider a coin tossing and think about its causal diagram, y1 to yn. It means that let's toss a coin n times, and each are node for each coin tossing. And you can think about n isolated or unconnected nodes for independent identical distribution. There are no arrows between nodes. However, the IID is not a single assumption, but a set of assumptions. For the n nodes, there are an n factorial dependence patterns between them. Think about the permutation of them. However, we have suppose we have observation of that n coin tossing. We have just n observational data about them. The dependency grows much faster than the number of observation n. When even we have more observation, we cannot fully capture the n factorial dependence patterns between the nodes or each coin tossing. So the amount of deductive information in this assumption, the IID assumption set, is beyond data alone could contain. Only background design information, whether the cost is randomly tossed or not, kind of thing, can supply enough information to warrant the IID assumption. So the author says that even for this simple coin tossing assumption, we need to think about causal components behind it. Causal component behind it. So not only for like some complicating structure equation behind it, like but even for the IID assumption, we need some kind of we need to think about some kind of causal component behind it.
Okay, I'm trying to understand. I think he says that this assumption of IID is causal in some sense, or the fact that you make this assumption, it's like making a causal a diagram where you have a causal assumption that you have a diagram with n nodes that are without arrows. And this is actually a causal model. And that's it?
Yes, and to ensure that these examples satisfies the IID assumption, we need beyond the observation, but we need some kind of causal components to ensure that this observation comes from like some randomized trial.
Okay.
So consider again the descriptive or decision analysis. Only physical action blocking all causal effects on selection or treatment can provide deductive justification for the entire set of assumptions corresponding to independence.
Okay, what was that? So only the physical actions of blocking all causal effects on selection can provide deductive justification for the entire. This is a statement. This is what he wants to convey. Okay, let's continue.
I did have a comment, maybe more of a question, Donghua. So these arguments for physical independence being necessary for probabilistic independence are assuming that our probabilities are in some sense physical events, right?
Yes, yes, yes.
Now you might think that one interpretation of probability is that it's not about frequencies that happen in the world, but instead about your own subjective degrees of belief, your credences, in which case this argument is, I think, orthogonal to the issue.
So you're saying that this, if we take the subjective interpretation, then this argument is not relevant to it. This argument is relevant to the frequencies
Right.
interpretation.
Right.
Okay.
Okay.
Okay, go on.
So the next part says that in human field studies, a selection indicator node S should be considered as a part of the data generating process. The selection node may be influenced by study variables. As we seen before, like some characteristics of the voters can influence the node S. And by definition, only samples with S equal 1 are observed. So every causal node actually is always conditioned on S equal 1. Even further, if S is affected by more than one variable, then it is a conditioned collider. So that is a source for potential bias, because a collider should not be conditioned for to block the to remove the bias in that causal graph. However, this effect is often ignored in the studies. That is what the author says. And furthermore, even the selection bias may arise when S is not a collider. Actually, this is the example we already seen before. S is just a node, not a collider in this graph. However, because the S is conditioned on, another node C opens the vector path from S to V. So we need to think about the bias of that path to estimate the probability of V. And actually, as we learned, the bias can be adjusted by the by condition on C, because we can block that path, that vector path by blocking C. And however, by blocking that node, we can only obtain C conditional distribution of V. So to obtain the marginal C unconditional distribution of V, we have to, or we can integrate out that C variable, and we can obtain the marginal distribution of V. So when S is collider, we can easily see that it can cause a bias. However, even for that case of S is not a collider, it also causes a bias, and we need to think about how to adjust that bias by some kind of conditioning or reweighting, which we saw before. And a parallel example of the selection bias for the treatment effect analysis. Think about X is a treatment, Y is the income, and C is a modifier of Y. Even in that case as well, we can only observe some observed samples from the population. So even though C is independent of X and Y is independent of S given C, but the path SC to Y is always open by conditioning of S equal 1. So that causes a bias estimating the treatment effect of X on X, treatment effect of X on Y, given conditioning on S equal 1. So we need to always think about that part as well, and have to adjust that bias to obtain unbiased estimate of the treatment effect. And therefore, the author argues that valid statistical analysis is closer to the core. The core problem is about factoring causing the differences in distribution of targeted and those observed. For example, voters are the targeted population, and survey responders are the observed in descriptive analysis. And patient with a given indicator like X equal 1, the treatment, the potential outcomes of the potential of outcomes of the treatment are targeted. However, the actual patient in a trial are observed. So we need to think about that difference in distribution of those two different variables. So without a causal model, we do not have basis to connect the probability calculations of the observations and the real world. So the causal models are kind of connection between the two parts. So statistics is laying out the causal. The author argues that statistics is laying out the causal sequence of leading from the data to inference and decisions. And the outputs of the statistical analysis are physically justified only when it is deducted from the causal structure of the generator. So only the causal explanation provide the contextual justification for the probability models used in the analysis, displaying information about study features that physically constrain the data generation. So the researcher should understand and learn the causal thinking for the probability and mathematical statistics. And the author argues that introductory statistics should cover basic logics and its causal extensions for teaching mathematical statistic theories. So the causal relation is core to the statistics that is stated in the paper. From the next part, the author shows some history of the causal theories and argues some more about why the causal relation is a causal theory is a foundation for the frequentism or Bayesianism or objective statistics. Let's talk about the history, brief history of the causal theory. Causation in 2000th century statistics. Foundations of causation dates back to early 20th century. Neyman in 1923 paper proposed the concept of concept of potential outcomes. Those are not that part usually unnoticed. However, the potential outcome models entered the statistics journals from the 1930s as well. And in the early stage of the causal models, statistical development in early 20th centuries were foremost concerned with causal inferences derived from physical randomization. So I think that this part means that the concepts of potential outcomes or causal theories mainly discussed in randomized controlled trial RCT models. Fisher lay out potential outcomes clearly in his 1930s papers, and those are formalized by other statisticians later into potential outcome models in 20th centuries. And however, the author shows that the causal theory can also be able to include important mistakes, even while successfully predicting intervention effects. One of the examples is malaria. The word malaria itself coming from like old Italian meaning bad air. People thought that malaria rates were higher near swamp, so people attribute the malaria to toxic air. The causal model for that part is swamp causes toxic air, and it causes malaria. So people believe that toxic air causes malaria, and also it led to successful intervention such as draining swamps or building elevated houses. Actually, it reduced the malaria rates. So people believe that the cause of malaria is toxic air. However, even that causal model successfully predicts the malaria rates. However, it missed the actual causal structure. Actually, the malaria does not come from toxic air, but it comes from mosquito exposure. So this example shows that the swamp intervention can test only swamp to malaria effect, not the intermediate pathways such as tox scare or mosquito exposure. Oh, excuse me. So this example shows that an intervention experiment provides evidence only on classes of mechanism, not on specific mechanisms. So even randomized controlled trial may not identify the actual causal effect. This applies even more strongly to passive observational studies, non-experimental studies, because extraction of information about treatment effect in observational studies require causal models for the physical data generation process that includes non-random variation sources beyond the treatment. So not only the treatment, not only the trial, but also observation itself has some kind of causal relationship, causal factors for the observation or selection. So we need to think about that part. Any questions?
So what is that, the last sentence, what is does it relate to in the example that you gave? Extraction. So what should be done, should have been done differently? Or...
I think that this part is not very related to what we should have to do for this experiment. But even for the experimental studies, does not capture, cannot fully capture the actual causal effect. However, for the observational study, there are one more steps for the selection in the observation. So we have to think about that part as well for the observation studies. That is what I understand for this part. Okay, and actually, honestly, I do not fully understand the next part about relating causality to traditional statistical philosophies and objective statistics. The authors talk about the relationship between causal theory and frequentism and Bayesianism, and further for objective statistics. And I think that the authors argues that causal theories are can be core foundation for each of the philosophy or objective statistics. However, I think because that is because I do not have sufficient background about the statistical philosophy for the frequentism or Bayesian, especially for the Bayesianism. So I cannot fully understand what is the reasoning behind it.
I think that's related to the comment that Bruce said
earlier.
Yes. He claims here that the causal causality is the causal theories would be can explain both the frequentist approach, which comes from physical words and counting, and also Bayesianism. That's, I mean, from what I see in your slide, are incomplete both as learning theories and as philosophies of statistics, and sufficient for all sound applications. And he said, well, both can benefit from including causal information explicitly. Many statisticians assign primacy to objective model component. Okay, that's fine. Or you can continue with your last slide then. I don't have anything to say. I also cannot really comment on that.
Okay. So in conclusion, statistical science requires realistic causal models to analyze data, for the generation of the data and deduction of their empirical consequences. Decision analysis further requires further causal analysis to explain various pathways between treatment and outcomes. So causal foundation is essential for teaching and application of statistics. So basically, what the author wants to say is that causal theory is very important for the statistics, and we have to think about that part always, for especially for the application of the statistics to real world data. Yeah.
Okay, any questions? I think that was a challenging paper. I tried to read it. It's very unclear. But you did a good job of bringing the points. Okay, thank you very much.
Thank you very much.
And we are going to meet again on Friday. And following Monday is holiday. As you know, I forgot that. But so we, in the last week, we will have presentation only on Wednesday and Friday. So see you on Friday then. Bye bye. Yeah, let me just finish.
Professor?
Yes.